Okay, so section 4.2 is more of the same, direct proofs and some counterexamples, contradictions, things of that nature. But instead of dealing with odds and evens, we're going to talk about rational numbers. Remember, a rational number can be written as a ratio of two integers. Okay, where of course b better not be 0, otherwise we're screwed. Yeah. And so typically to write it, we write r as rational if and only if, right? There exist integers a and b, integers a and b. What the heck does that even say? A and b, such that r equals a over b, b not 0. Okay, so we've said that before. Okay, the kind of rational numbers, obviously fractions, but so are whole numbers, integers, and that sort of thing. Recall, maybe back in the day, you've seen this box, and so you had the whole the natural numbers, so that's 1 to 9, and the whole numbers 0 to 9, and then it keeps going, of course. And then integers are the negatives and positives, we call those the z's. And then outside of those are rational numbers, right? So these were the fractions and decimals live. However, everything inside of the rationals is irrational. So natural numbers are rational. 6 is 18 over 3, for instance. Okay? And so it's also 6 over 1. It's also, 50 or something over something. So idea is it can be done. Okay? So rational numbers. Okay, of course, these are irrationals. Irrationals, things like square root of 2, square root of 3, pi, that sort of thing, e, all those good guys. Yeah. So clearly we're going to be trying to see if we can wrap a problem into, can we pound it? So instead of pounding it into summation and making it look like 2k or 2k plus 1, we're going to try to pound it into summation as a over b. All right, cool. Recall that if you have two numbers and their product is 0, what do you know about that? Either a equals 0 or b equals 0 or both. Okay, that's the 0 product. Not a big deal. We talked about already that every integer is a rational number. Okay. Likewise, if a times b does not equal 0, then what does that mean? If that's the case, then neither a nor b is 0. So that's just the opposite of saying that. Negated it. Okay. We're going to talk a little bit now about this, and then this will be the kind of the thing that I'm going to launch off from. And that's when you talk about addition. Okay, let's think about this for a minute. If you add two integers, what will you get? Well, 7 plus 5 is 12, but that's what is it? That's an integer. Oh, that's right. And you get an integer. And the interesting part about that is what that says to us is that addition is closed under addition in the integers. So in other words, you start with an integer, you will by God get done with integers. If you take two integers, you're going to get an integer. Now that's true for addition, subtraction. If you subtract two integers, that's also true. And multiplication. All three of them are closed under the integers. Okay? Times two integers, you'll get an integer. Subtract two integers, you'll get an integer. Oh. Is that true for whole numbers? No. 5 plus 7 is 12. 12 is not a whole number. 12 is, not a natural number. Okay? So addition of whole numbers will give you a whole number. 2 plus 12 is 14. That's cool. 14 is a whole number. That's awesome. Subtraction, that's not true, because if you did 14 minus 2, you would get a whole number. That's true. But if you did 2 minus 14, you would not get a whole number. So we'd say subtraction is not closed for the whole numbers. Okay? And ditto for the integers and so on. Okay? Natural numbers. Natural numbers, it's not closed for addition, because 2 plus 9 is 11. That's not going to work. That doesn't give you a natural number. That is a number 1 to 9. It's also not closed under subtraction because 2 minus 7 is negative, and that's a problem. It's also not closed under multiplication because like 4 times 3 is 12, which is not a natural number. Okay? So closed, when you say something is closed, it means if you start with 2 of whatever it is you're talking about, you will always guaranteed to get back to the same thing you started with. Okay? So I want to look at multiplication for a minute. If a is an integer and b is an integer, a times b will also be an integer. And that's what that means to say that it's closed under, you will be an integer, so it's closed under multiplication. Integers are closed under multiplication. Cool. However, if you do a divided by b, 12 divided by 2. 12 divided by 2 happens to be 6. Is this an integer? It sure is. It sure is. What if I did 12 divided by 7? Ooh, you know what that's not, friend? That's not an integer. And so because it's not an integer, we would say that the integers are not closed under division. That is, the idea if you divide 2 integers, there's no guarantee you're going to get an integer back. In fact, you will most of the time not get an integer back. Okay? And so keep that in mind. The only way you get an integer back is if you happen to divide by one of the factors. Okay? And so just think about that. Even a number like 48, which has a gazillion factors, it has a lot more non-factors. I mean, think about that for a minute. Let's see here. 48. Cool. So the factors of 48, of course, are plus and minus 1, plus and minus 2. 1 doesn't really count. I'm not going to worry about 1. So because, you know, if you divide by 1, you get 48. Well, I guess I'll do it. That's fine. 2 plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 16, plus or minus 24, plus or minus 48. Now, that's 1. Let's just stay on the positive side of things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers between 1 and 48 that are integers that will give you a perfect integer value. So, for instance, 48 divided by 24 gives you 2. Awesome. There's 10 of those numbers. However, between 1 and 48, I believe there's 48 numbers. So that means the other 38 of them don't work. And so keep that in mind. And then you're like, well, could I go bigger than 48? You can. 50 is a number bigger than 48. 48 divided by 50 is going to be a fraction, which means it's not going to be an integer. So in fact, there's always going to be way more numbers, integers, that will give you rational answers than there is ones that will give you, integer values when you divide. Okay, so just be aware of that. It's pretty straightforward, but the idea of closed, and we talk about that in number theory, is that when you look at a group of numbers, be it the integers or what have you, when you say something is closed, that means when you use that operation and you start with 2 things in that group, say integers, and you do addition, let's say, you are guaranteed, because it's closed, you're guaranteed to get another integer back out. That's what closed means. Okay? And check this out. What happens? Here's my question to you. What about the rationals? If you add rationals, what will you get? You get a rational. That's right. Nice. And if you subtract rationals, you will get rationals. And if you multiply, you will get, that's right, rationals. And if you divide, wait, Jay, you mean like A over B divided by C over D? That's correct. And when I do that, that's the same as saying AB times D over C. That's right. And so in this case, clearly from the start, B better not be 0. We'd have a problem. D better not be 0. And C, of course, better also not be 0. Otherwise, we're also screwed. All right, but if I do all that, what are you going to get? Well, that is AD over BC. Hey, what do you know? This is an integer times an integer is an integer. That's cool. Integer. And an integer times an integer is an integer. And the ratio of 2 integers is rational. Nice. So what does that tell me? It tells me that division is also closed. All 4 of these are closed in the rationals. Okay? So just be aware of that. That's always going to be true. Now, specifically, for some stupid reason, your book tells you this corollary. Dude, did you know that if you double a rational number, you get a rational number? Yeah. But what are you doing when you're timesing by 2? You're multiplying by a rational number. Multiplication is closed under the rationals, so you're good to go. Okay. So yeah, big surprise there. Okay. It may have been a while since you've seen this cute little trick. If you're going to write this guy, here as a repeating, as you're going to write that as a fraction. Remember, so another way to say a rational number, you can write as a over b. It's also a terminating or repeating decimal. Okay, so to do this, the way to do it, you just write like this. Oops. Yada, yada, yada. And then because there's 2 digits that repeat, you're going to multiply it by 100 for 2 decimal places. You're going to get 37.37 forever. And when you subtract, what will you get? You will get 99x on this side. And when you subtract on this side, you'll get 37. And when you divide, you will get 37 over 99. Bam. Likewise, we know that 1/3. We know that 1/3 is equal to 0.33333. Well, let's think about why. Okay, there's 1 digit that repeats. So if you let x equal 0.33333, and so because there's 1 digit, you multiply by 10. And when you subtract, you'll get 9x is equal to 3. So x is 3/9 or 1/3. Now, bear in mind then, if you saw 0.99999, you're like, oh, weird. That's 3 times this. Well, it should be 3 times 1/3. 3 times 1/3 is 1. That's right. So you could write it like this, and you could then do this. Remember, that goes on forever. So the idea is that when you subtract, you're going to get 9x is equal to 9. X is equal to 1. Okay. But if you do 99999 forever, what you're saying is, that's 1. Okay, that always bothered me a little bit when I was a kid, but not terribly difficult to do. Yeah, just in case you've forgotten that, it's been a while since you've seen that. Good enough. Okay. So number 16 here in the book, the quotient of any 2 rational numbers is a rational number. Yeah, that's true. Now, why is that true? So when I did that, we already kind of looked at that one, but let's go ahead and run through it again. So if you have a over b, so when I look at this guy, obviously b not equals 0. Okay, and c over d, of course, d not equals 0. So if I take the quotient of these 2 guys, okay, because I'm doing this, because this guy in the bottom, this guy can't be 0, the only way for this denominator to be 0 is if c equals 0. So we must also write c not equal to 0 in this case. And so when I do this, I need you to write it like this. Just like last time, they wanted me to do a quotient. Well, by God, I'm doing a quotient. Look at me go. Cool. So what do I get? Well, I get AD on top over BC on the bottom. And what do we know about multiplication for the integers? An integer times an integer is an integer. I'll call it EF. Let's call it F. And I will call this G or something. And I know that F and G are integers. F and G are integers. And what I want you to do is just spell it out for me. Because multiplication is closed for integers. Okay? Hence, f over g by definition is irrational. A rational number. Okay? That's the kind of proof I want. I don't want a long, drawn-out thing, but I want to be able to follow a person's logic through them. Okay? Check this out. If r and s are any 2 rational numbers, r plus s over 2 is rational. All right, so r and s are rational. Cool. So then r plus s over 2 is rational. I want to know, how would I prove that? I don't know. Let's find out. So when I do this, okay, what do I know here? Well, first of all, this is a quotient already of two. It's a quotient right now of two rational numbers. I want you to be aware of that in just a minute, okay? So when I look at this, I say R plus S is rational. R plus S is rational because the rationals are closed under addition. Okay, to add a rational to a rational, you will get a rational, period. And then, because that guy right there is rational, R plus S, 2 is also rational. And so we know this has to be rational because division is closed for the rationals. Now, I can say either way. I don't really care which way you write it. Sometimes I write it one way, sometimes I write it the other way. It's a closed process, okay? Division is a closed process for the rationals. If you start with a rational, you divide, you will get a rational, which is the one thing we just proved in a second, okay? Let's try this guy here. This sounds fun. So if R is rational, then 3R squared minus 2R plus 4 is rational. Okay? So you know that this has to be true, but let's think about why that has to be true, okay? So when I do this, I think to myself, well, wait a minute. If I take a right here, if I take a rational times a rational, R squared is rational. Why? Because rationals are closed under multiplication. That same process will mean that 3R squared, for the ditto reason, and so is 2R for the ditto reason, yes? And therefore, if you take 3R squared minus 2R, okay, plus 4, that's because rationals are closed under addition and subtraction. There's a T in there somewhere. Cool. Okay. Now you're like, Jay, could you do it a different way? Could you do me a little bit of mathematics to just have fun? I said, sure, let's do it, man. I love it. Of course, B not 0. Minus 4R, is that what I said? By God, no, it's 2R minus 2R plus 4. Plus 4. Oops, but R is A over B, you dope. Nice. So if I do this, that'd be 3A squared over B squared minus 2A over B plus 4, sure. Let's get a common denominator, shall we? By the way, I'm not sure that this is helpful or not. I guess we'll try it and see if I like it. Over B squared. Okay, again, B still not 0. Cool. If I look at that guy, I'm like, wait, that's interesting. Weird. Fascinating. Again, same basic premise. A is a rational number, or A is an integer, yes? A is an integer. When you square an integer, what are you going to get? An integer. Times it by 3, what are you going to get? You're going to get an integer. Integer times integer times integer is integer. Integer squared is integer. Integer minus integer plus integer is integer. Over integer, that is by George the definition of a rational function. If you'd like to run through it like that, you are more than welcome to. Help yourself. I would like to look at this for just a minute, if you don't mind. That is 3A and 1A. If you were to factor it, B and B, I believe, and minus and minus. No, it doesn't factor, does it? That's weird. Oh, there's a 4 there, you moron. I was going to say, I knew it had to factor. Let's back up and try again, shall we? Okay. Okay. I don't know if it factors or not. Let's see. 2 plus minus square root of 4 minus 48. No, it doesn't factor, does it? It doesn't factor. Never mind. I thought it factored. I was going to get excited for a minute because I was going to show you something, but it doesn't factor. No, well, whatever. I was excited. You know, it was kind of neato, I guess. Interesting. This right here has to do with what's called the rational root theorem. You may have learned back in the day in like Algebra 2 class when you were sitting there busy solving these suckers all day long. What are the possible roots of this guy? Well, what they are factors of this dude divided by factors of this guy. Think about why that is. This factors thusly. Factors of 9 are 3 and 3. Plus and plus, it has to be this time. And so check it out. If you were to do this, it's x plus 3 equals 0. So to subtract, you get 3 over 1. That's what x has to be, negative 3 over 1. Okay. Likewise, if you had this guy here, let's say 2x squared minus, don't peek, I'm going to do this one ahead of time here. I'm just going to like do it and see what happens, man. Whatever, 6x squared minus 14 minus 26x plus 28 equals a goose egg. So you do this, you're like, geez, I don't know, what are the factors of 6x? Well, there's 6x and 1x. There's 3x and 2x. Maybe I go with those ones first. I got to try them all. I could use 28 and 1. I could use 14 and 2. I could use 7 and 4. Those are the factors of 28. Geez, I feel like I'll use 7 and 4. I wonder if this will work. Probably if you did it the right way, it would. You moron. Oh, look at that. It works. But check it out, friend. The roots are equal to this. And what is that number, my friend? That is a rational root. What is this number, my friend? Why, it's a rational root. What is 7? Why, it's a factor of 28. What is 3? By George, it's a factor of 6. That's where that rational root theorem comes from. That's the only way that's going to happen, because when you solve this, what are you going to do? You're going to do an algebra problem where you take the factor of this guy divided by the factor of this guy. That's the only way it's ever going to happen, if the root is rational. Now, if it doesn't factor and it comes out the square root of 7, that's not a rational root, so that won't hold true for something that's not a rational root. Okay? True or false? A is odd, then a squared plus a is even. A is odd. A squared plus a is even. True or false? True or false? I don't know. I know that a is equal to 2k plus 1, so let's go to work. You want me to square it? I'll square it, friend. Oops. And then I'll add it. Nice. Let's go. So if I do this, I'm going to get 4k squared plus 4k plus 1 plus 2k plus 1. Am I right? I feel like I'm right. Okay. So then when I do this here, what I'm going to get? Well, I'm going to get, well, I feel like that's 2k. Well, actually, let's do this. Let's pull a 2 out of that. Let's write it as 2 times 2k squared plus 2 times 2k plus another k. So there's actually 3 of those 2k's, right? Yeah. Yep. Plus 2. Well, that's hot. And what is 2? Well, 2 is an even number. So this is an even number. By definition, this is an even number. And by definition, 2 times a value is also an even number. So an even plus an even plus an even is an even. Now you're like, could I do it better than that, Jay? Yeah, you can. Watch this. 4k squared plus 6k plus what? Plus 2, you moron. Cool. And if you're careful, what do they have in common? They got 2 in common. And what are you left with? You're left with 2k squared plus 3k plus 1. What does this look like to you? If k is an integer, then 3 times an integer is an integer. An integer squared is an integer times 2 is an integer plus 1 is an integer. This looks an awful lot like 2z to me. Am I right? And what is 2z? 2z is even. Okay? If you can show me that and work your way through it with a little bit of I was talking, but if you'd like to write those answers down, that's kind of how I'd like to see it done. Okay. We'll try this one here. Never tried this one before, I don't think, anyway. Let's see. True or false? K is even. M is odd. Nice. K plus 2 squared minus M minus 1 squared is even. All right, take your bets, friends. Take your bets. Place your bets. Here we go. I don't know. Let's go have some fun. What is K? K is even. So, I don't know. K can be written as 2R, I guess. All right? So, I'm just going to put that in. I'm going to write 2R, because that means it's even, plus 2 squared. And then, what do I got here? Well, I don't know. Minus. And then, the M is odd. Well, all right. So, let's just say M is equal to 2Q plus 1. Sweet. 2Q plus 1 minus 1 squared. Well, that's hot. So this is going to be 2Q square. This is going to be 2. Well, I can do it a couple different ways. I don't know that that makes any difference to me. Let's do. Do I want to FOIL it out? I'll take a 2 out. I'll take a 2 out. I'll take a 2 out. Take a 2 out. Take a 2 out. I'll FOIL it first. How about that? So it's 4R squared plus 8R plus 4. Yeah, I kind of dig that. This is really just like, I'm going to write this as 4Q squared, if that's okay with you. I'm going to do it anyways. I don't really care. Nice. And I think I'm going to write them as 4R squared minus Q squared plus 8R plus 4. And then I think I'm going to take a 2 out of all of those dudes. Oops. That's an integer. 4 times an integer is an integer. An integer squared is still an integer. An integer squared is still an integer. The difference of integers are an integer times an integer is an integer. That means this whole shebang in there is an integer. And 2 times an integer, by definition, is even. Okay? Pretty sure we knew that going in. If you have a start with an even integer and you add 2 to it, what do you get? Well, you get an even integer. When you square an even integer, like say 4 or 8 or 32, what are you going to get? An even integer. When you take an odd integer and you subtract 1, all of a sudden you went from 5 to 4, 7 to 6, what have you. You went from an odd to an even. An even squared is an even. An even number minus an even number is going to be what? An even number. How do I know that? Because if the one even number was 2K and the other even number was 2M, well, I don't want to do 2K, that's what we're using for 2J minus 2B or something. Well, that's the same as saying 2J minus B. And what is J minus B by definition? That is an integer. And that, my friends, is even. Okay? That's the sort of thing that I want you doing in section 4.2. I want you using the thought processes. I want you showing what's going on, and then go to town from there and see what happens. Okay? Explain to me what it is you're doing. So in other words, you come into that situation, you're like, oh, sweet. You know what this has to be? This has to be here's what an odd means. 2K plus 1. Sweet, let's stick it in. Ooh, it's an integer. It's A over B. Sweet, B not equal to 0. And just keep doing these situations until you get down to the answer that you were searching for. Remember, you knew in this last case it had to be even. So you're trying to beat that thing into submission and make it look something like this guy. If you can do that algebraically, bam, you've showed that it has to be an even number. Okay? Good luck.